Welcome to the second part of first lecture. In this lecture, we learn what is walk, what is trail, path, cycles in a graph. We will learn when a graph is said to be connected graph, and also we learn what is a complement of a graph and some related results. Let me start with walk in a graph. So, the definition here. So, walk in a graph or multigraph So, multigraph means so here multiple parallel edges and loops are allowed, and simple graph parallel edges and loops are not allowed. So, a walk in a graph or multigraph is an alternating sequence of vertices and edges V naught E1, V1, E2, V2 like this, and then V n minus 1, E n, V n, beginning and ending with vertices. So, the sequence begins with a vertex and end with a vertex, and such that this E I is basically an edge joining V I minus 1 V I. Okay. So, this walk joins V naught and V n, and it is called V naught V n walk. And a walk is closed if the first vertex is equal to the last vertex, otherwise open walk. So, this walk, it is a trail if all these edges are distinct, if the edges are distinct. I will explain using an example, and this walk, it is a path, this walk is a path if the vertices are distinct, and hence the edges are also distinct. If V naught, these are very important because these definitions we will be using throughout this course. V naught equal to V n, but all other vertices are distinct, then it is a cycle. Okay. So, I will explain this definitions using this example maybe. So, let me just give an example of a walk, say V 1 V 5 walk. So, you start with V 1 and then go to V 2 with say any one edge, say E 2, and then you go to V 2, and then from V 2 you go to V 3 using the edge E 3, V 3. Please note that we are using this edge also because there could be multiple edges between two vertices, like here there are two edges between V 1 and V 2. So, which edge you use here to denote that we write the edge labels in this sequence also. So, V 3, then E 4, you go to V 4 and then again use E 4 to come to V 3, and then you go to V 5 using E 5, P 5. So, this is a walk, and this is a walk because of course, you can see that the same edge appearing twice. So, this is not a trail. Okay. Now, V 1 V 5 trail could be like this: V 1 E 2 V 3 E 5 V 5. So, this is a trail because all the edges are distinct here, and this is also a path because all the vertices are also distinct. And let me just give one more example of a cycle maybe. So, this is a cycle. If you so in the case of cycle, this first vertex will be equal to the last vertex. So, V 1 E 2 V 3 E 5 V 5 and then sorry E 7 V 1. So, this is a cycle, right. Now, we talk about when a graph is connected. A graph is connected if every pair of vertices are joined by a path. If a graph is not connected, then it is called a disconnected graph. And its maximal connected subgraphs are called components. Okay. So, of course, the graph that we had before, say for example, this graph, this is a connected graph because there exists a path between every pair of vertices. Say if I take this vertex and this vertex, there is a path, they are not adjacent, but there is a path between these two vertices. Now, and this is true for any pair of vertices. And now, if I add another edge here or two vertices here, and this is my graph now, this is my graph G. Now, you can see that there is no path from this vertex to this vertex. So, this graph is disconnected graph. Okay. So, the G is disconnected and it has two components. Okay. So, this is one component, this is the maximal connected subgraph of this graph, and the other component is this one. So, if a graph is disconnected, then it has at least two components. Now, we talk about a result theorem. Let G be a graph of order n. The graph of order n means it has n vertices. If degree of u plus the degree of v is greater than equal to n minus 1 for every two non-adjacent vertices u and v of G, then G is connected. Okay. So, this says that G is a graph of order n, it has n vertices. If the degree sum of two vertices, two non-adjacent vertices u and v, if the degree sum is greater than or equal to n minus 1, then the graph is connected graph. Okay. So, let us prove this theorem. so we need to prove that every two vertices of G are connected by a path. In order to prove a graph is connected, what you have to do is that you have to prove that every pair of vertices in the graph are joined by a path. Okay? So, that is what we have to do here. Now, first let x and y be two vertices of G. The first case is that if x and y are adjacent, that means there is an edge between x and y, like this is x, this is y, then there is a path. So, this is a path of length 1. So, you are done basically. That means x and y are adjacent. So, assume that x and y, assume that x and y are non-adjacent. That means there is no path between, there is no edge between x and y. Then okay, so let me draw the figure. This is x, this is y, and they are not adjacent. For the sake of simplicity or to understand, suppose n is equal to say 6, there are 6 vertices in the graph. So, these are the other 4 vertices in the graph. Okay. Now, the degree sum is according to this theorem, the degree of x plus the degree of y is equal to, is greater than or equal to 5. Now, suppose the degree of x is 3 and degree of y is 2. See, x and y are not adjacent, then x degree 3, x, suppose x is adjacent to this one and this one, fine. So, the degree of x is 3. Now, the degree of y is 2. So, then y is again can't be adjacent to x because x and y is not an edge. So, y can be adjacent to this, but y has to be adjacent to another vertex, suppose this one. Okay. Now, what we claim is that the degree of x plus the degree of y greater than equal to n minus 1 implies there must be a vertex in general V I that is adjacent to both x and y, and that Vk is this one. This is what let me call them V1, V2, V3, V4. So, in this example this Vi is V3 basically, and this has to be true because the degree sum is greater than or equal to n minus 1. And another way of understanding this fact is this is called Pigeon hole principle. It says that if n plus 1 pigeons are put into n holes, then at least one hole contains 2 or more pigeons. So, this is a very well known fact. So, here in terms of pigeonhole principle, if you want to understand this one, so you have 4 pigeons, you have 4 holes. So, every vertex is like a hole, and one edge is corresponds to one pigeon coming here. So, since there are 5 pigeons, because 5 edges are there and 4 holes. So, at least one hole contains 2 pigeons. That is what it will be true in general. Okay, so, what we understood is that this implies there must be a vertex Vi that is adjacent to both x and y. So, x Vi y is a path of length 2. I did not say what is path of length, what is the length of a path. So, it has 2 edges in this path. So, I omitted the edge now because anyway the sequence of vertices are enough. So, there are 2 edges. So, that is why the length of this path is 2. Okay. So, we proved that when x and y are not an edge, there is a path of length 2 or there is a path between x and y always. So, so we have finally proved that G is connected. Okay. Now, this is another result of or theorem you can say. This can be proved similar way. If G is a graph of order n with minimum degree greater than equal to n minus 1 by 2, then G is connected. So, the proof is very obvious from the previous result. Here for every 2 non-adjacent vertices, say u and v, what we have that the degree of u plus the degree of v is greater than equal to n minus 1 by 2 plus n minus 1 by 2, because the minimum degree is greater than or equal to n minus 1 by 2. So, sum of these two degrees is greater than equal to n minus 1. So, using the previous theorem, G is connected. Okay. Well, so next we talk about complement of a graph. Complement of a graph G, denoted by G complement has the same set of vertices as G, but two vertices are adjacent in G complement if and only if they are not adjacent in G. So, let me just give a small example. Suppose this is the graph G. Let me label them A, B, C, D. This is my graph G. And then what is G complement? Is it has the same set of vertices A, B, C and D. Now, A and D will be adjacent because they are not adjacent in G. A and C will be adjacent because they are not adjacent in G. Similarly, B and D will be adjacent because they are not adjacent in G. So, this is what the G complement is. Now, let me prove a theorem. If G is disconnected graph, then G complement is connected. Okay, so, I will just give the outline of proof. Okay, so, if U and V are two vertices in the graph G, this is the set of vertices in the graph G notation, we must find a path in G complement joining U and V. Right? Because as I said, to prove that any graph is connected, you have to prove that there exists a path between every pair of vertices. So, we took a pair of vertices U and V, and then we have to prove that there is a path between U and V in G complement. So, the case 1 is that U and V are in two different components of G. G is disconnected graph. So, the first case is that U is a vertex which is in one component of G and the other vertex V is in the another component of G. So, since they are in two different component, U and V are not adjacent in G, hence U and V are adjacent in G complement by the definition of G complement. So, there is a path of length 1 between U and V in G complement. The case 2 is that U and V are in the same component okay. So, in G they are in the same component. So, U is here and V is here. Now, there could be two cases if they are in the same component, but if U and V are not adjacent, then they will be adjacent in G complement. So, it is done. Suppose they are adjacent in G, right. So, they may or may not be adjacent in G. Now, suppose W is another vertex in the other component. Let W be a vertex in another component of G. Then W is neither adjacent to U nor adjacent to V. So, W will be in G complement. W is adjacent to both U and V, because they are not adjacent in G. So, they will be adjacent in G complement. Thus, there is a path U W V joining U and V in G complement. So, we took an arbitrary pair of vertices and then we proved that in both the cases there is a path between them. So, G complement is connected. Okay. In this lecture we have learned what is a connected graph and what is a complement of a graph, and then finally we proved that if G is disconnected graph, then G complement is a connected graph. Thank you very much.